Factorizing polynomials in VCE methods can seem very difficult, but let's break it down step by step and make it super simple. For this function here, we have f of x is equal to x cubed minus 3x squared minus 6x plus 18. So there's multiple ways of factorizing polynomials, and in particular, we're going to focus on cubics in this case. Now, a lot of you might have, if you've gone through content before, let's say last year or let's say this year as well, you might know the factor theorem, but the factor theorem is not always necessary. There's some cases where you can do a bit of an easier way of factorizing these polynomials or these cubics. And in this case, what we can actually use is something called grouping, which you might have learnt before. What grouping requires us to do is first of all have a specific type of equation that is, I would say, pretty simple. And we would also need to be able to recognize patterns in our polynomial. Now what I mean by that is we see x cubed minus 3x squared. So we can see this number, this coefficient of x squared is negative 3 times the coefficient of x cubed, which is just 1. And then here we have a number that is 3 times the previous one as well. So you can see there's some sort of pattern here, and that allows us to group the same bracket together. So what I mean by that is what we can say for this one is that this is the same as x squared outside of x minus 3. So what I've done is I've taken out x squared as a common term of these two terms here, and then I have x minus 3 as my remainder. And I could actually do the same thing here if I have, I think it would be minus 6. What would happen is that if we have x minus 3 in this bracket as well, what happens is that we have negative 6x minus 6 multiplied by negative 3, which becomes positive 18. But the goal of grouping is to get the same bracket in multiple terms. In this case, it's just 2. And then what happens is that this is going to equal x minus 3 outside of our coefficients, which is x squared minus 6. And you can imagine this is just backwards of expanding, because what we've done is when we do expand, we multiply all the terms inside one bracket with all the terms inside another. So this is just kind of like the intermediate process of expanding / factorizing. So this is not factorized yet, even though it looks like we have two brackets that look factorized. We can actually keep on factorizing this further to get linear factors. So x minus 3 is already linear, but then x squared minus 6 is not quite linear. But what we can do is use the difference of two squares. So it's going to be x plus the square root of 6, and then x minus the square root of 6. We're using difference of two squares even though we don't have a perfect square, but in order to get full factorization, we'll need to include our surds in this case. But this is not the standard way of factorizing cubics in most cases. This is for very rare cases where it's very easy to see a certain pattern. Most of the times we'll use the factor theorem, which we'll go through in the next part of this video. Now here's the most common type of cubic equation that we're going to get. It has no patterns, and we'll simply have to use the remainder theorem. Now let's just talk about quickly what the remainder theorem actually is. I realized I didn't mention it before, but what the remainder theorem suggests that if you substitute in a number into your function and that results in a 0, then that can tell us a bit of information about factors in our equation. So I'll give you an example just in a general sense actually, and let's actually do it for quadratics because it's a bit easier to understand for quadratics because we've done it before, but then the same logic applies to cubic equations. Let's just get a bit of a tissue to rub out what I'm going to write. But let's just say if we have f of x is equal to x minus 3, x minus 4. Now we know that if we have this equation equal to 0, this has two solutions. We have x equals 3 or x equals 4. We say or, but both of them are solutions to this equation. But what we know is that if we work backwards, we'll get exactly the same result. What I mean by that is if we substitute in f of 3 and we end up getting 0, so we substitute x equals 3, we end up getting 0 as a result, we know that x minus 3 is a factor. Okay? Now, yes, that's definitely the case. Now, if we also substitute in f of 4 is equal to 0, that means we know that x minus 4 is a factor as well. Now, we can combine these two together. We know we have two factors, and with other information, we would be able to find our full rule. So hopefully this makes sense. If you substitute in an x value and you end up getting 0, that x value is an intercept, and therefore x minus that value is going to be a factor. So that's pretty much the factor theorem for us, and we're going to apply the same logic to a cubic equation. Now you might be wondering, why don't we use the same process for a quadratic equation? And it's actually because quadratics are really easy to factorize relative to cubic equations, because we can just read off a quadratic equation and see, oh yeah, I know two numbers that multiply to 12, and I know two numbers that add up to -8. Therefore, I know my two factors, and therefore I can put everything into factorized form. It's not as simple for cubic equations because we don't have that ease of process where we can just see, okay, we have two numbers multiplying to get one number, and we have two numbers adding to get the other coefficient. We have multiple coefficients in this case, so it adds another layer of complexity. That's why we need a different process, and that's why we have the root theorem or the remainder theorem. Cool. So in this case, we have x cubed minus 3x squared minus 10x plus 24. Now, what we need to do is just figure out one x value that is going to give us one of our factors. Now, you might be thinking, there's infinitely many numbers. There's infinitely many whole numbers as well. There's infinitely many positive numbers. What numbers do we substitute in? What numbers do we try first to get one possible factor? Once we get one possible factor, you'll see that the process is a lot easier. But the first factor is always the hardest. Now, to pick factors that we use, we take the last value, which is the y-intercept. It's not the c value in this case, because we have ax cubed plus bx squared plus cx plus d. So in this case, the general coefficient that we use is d, but in general, it's just the y-intercept. We take the y-intercept and we take plus or minus of factors of this value. So we take positive and negative factors, and we should know why we can take negative factors as well. If we have -3 times -8, that ends up being positive 24. So that's why we need to consider the positive and negative of all the factors of 24. Now, 24 is kind of cruel because it has a lot of factors, but let's just write them all out. So we have 1, we have 2, we have 3, we have 4, we have 6, we have 8, we have 12, and we have 24 as our factors. Now what we do is we substitute in positives and negatives of all these numbers here until we hit one factor. We can actually keep going and get multiple factors, but most people just stop at getting one factor because 24 is a bit easier, but sometimes you do have larger numbers on the outside, which does make it more complicated. So the normal process goes just pick numbers until you find one factor, and that'll give us one, or until you get a 0 value, and that'll give us our first factor. So obviously we start off with 1 because that's really easy. A lot of the time you don't actually have to show working out, especially for, let's say if you have +1, it's pretty easy to substitute in, but let's just write it out. 1 cubed is 1, minus 3 times 1 squared is 1 minus 3, minus 10 multiplied by 1 is minus 10, plus 24 is equal to that. Cool. So this becomes 1 minus 3 minus 10 plus 24. You can just see that this is not going to be equal to 0, but if you want to calculate it, it'll be -2 minus 10, which is -12, plus 24 is equal to +12. I'm just going to say that's not equal to 0. We're not concerned what value it is. We're not concerned what non-zero value it is. If it's either 0 or not 0. So that's why I just straight away say not 0. We don't really care about it. Now let's substitute in -1 as well, just to confirm that doesn't equal. But a lot of the times, you can just skip numbers, especially when you become more experienced. So if I look at this, I'm going to see that -1 won't work either, because this will be -1 multiplied plus 3 plus 10 plus 24. The number's too positive, so I'm just going to straight away see this is not equal to 0. Cool. Let's try out f of 2. So we end up getting 2 cubed, which is 8. Minus 3 times 2 squared, which is 3 times 4, minus 10 multiplied by 2, plus 24. This might work, we'll just calculate it. 8 minus 12 is -24, minus 12 is not -24, 8 minus 12 is -4, minus 20 plus 24 is equal to 0. Perfect. So f of 2 is equal to 0. Therefore, x minus 2 is a factor. Awesome. So we know one of our factors now, which is awesome news, because now we just need 2 more factors. So we can keep substituting these numbers in, but as you can see, it's pretty tedious to try them all out. And that's another reason why we don't do that part of the process. We just get one factor, and then we have an alternate process to get the other factors, or just the remaining polynomial outside of the equation. So we know that f of x is equal to x cubed minus 3x squared minus 10x plus 24, and that's going to be equal to x minus 2 outside of this unknown polynomial here. So we need to get this polynomial here, and we know from intuition that this is going to be quadratic as well, just to keep that in mind, because we have something linear multiplied by something quadratic to get to something cubic, because this is a degree 3 polynomial. is equal to a degree 1 polynomial multiplied by a degree 2 polynomial. So this quadratic is what we want to aim to get, and eventually in the long term we want to be able to factorize this quadratic as well to get a full factorized equation with 3 linear factors, if that's actually possible. Sometimes this is actually not the case, but I've set this up in a way that it is to make it easier to learn. Awesome. So how do we get the remaining quadratic? We probably need a bit more space, so I might just rub this out and then we'll continue from there. Okay, so in the previous video, we found that f of 2 was equal to 0, and therefore we could say that x minus 2 is a factor of our polynomial. Now there's 2 ways of getting the remaining quadratic, which will give us our further 2 factors that are outside of x minus 2. The first way is doing something called long division. You probably know what long division is already. You might have learned it in primary school or early high school as well. Personally, I've got how to do it when it's just numbers. I only know how to do it when we have polynomials, which is kind of weird because technically it is harder. But anyway, we can do long division with polynomials, which is what I'll teach you how to do now. Because essentially what we have is, I wrote it down on the previous whiteboard in the previous part of the video, but this function is going to be equal to x minus 2 outside of a quadratic, right? So what we can actually do is take this polynomial, divide it by x minus 2, and that's going to leave us with our remaining quadratic, which is actually what we want. And the only way of actually getting there is through long division if we don't have a calculator. So we need to perform long division by hand. Sorry, a correction. It's not the only way, but it's the only way that we're able to just divide like a normal expression. So we use long division to actually do that process. So if you don't know what long division usually looks like, it's something along the lines of this, where you have what you start with at the bottom here. So x cubed minus 3x squared minus 10x plus 24. And then you have x minus 2 on the outside there. I'm just going to check that this is visible on the other screen. Yes, it is. Perfect. So we're taking this polynomial here, this cubic, and we're dividing by x minus 2. Now the first step is to take this term here and divide it by the leading term of what we're dividing. So in this case, it's going to be x cubed divided by x. That is going to be equal to x squared, and that goes at the top there. So x squared is our first term in our remainder. So what we then do is we take this x squared and we multiply it by this whole bracket here, or this whole divisor here. So x squared multiplied by x minus 2 multiplied by x squared. And we put that underneath this term here. So what we're going to do is take x squared times by x, which is x cubed, and then x squared multiplied by negative 2 becomes negative 2x squared, like that. Now the point of that was to get this expression here, which we're going to minus from the leading expression. So we're going to minus them from each other. And the goal is that the leading term is going to cancel out, and then we're going to have a remaining term here, and that indirectly goes up there. You'll see how it works. So x cubed again cancels out. X cubed minus x cubed is equal to 0. We could just write 0x cubed if we want. And then negative 3x squared minus negative 2x squared, so it becomes negative 3x squared plus 2x squared, just becomes a minus 1x squared. So we're just going to write minus x squared there. Awesome. Now what we do is we take this minus x squared, we divide it by the leading term there, minus x squared divided by x becomes minus x, and we put that at the top there. So we take this term here, divide it by the leading term, and that becomes our new value in our remaining quotient. I think I forgot the terms, but this is what we're left with by the end of it. So we take this term here, negative x squared divided by x, we end up getting minus x as well. Then we repeat the process again. We take minus x and we multiply it with this bracket here. So we end up getting minus x squared, and you can see perfect, they cancel out. They're meant to be the same. So when you subtract it, they do cancel out. And then minus x multiplied by negative 2, which becomes positive 2x. Now you can see that there's this gap here. What you do is you bring this number down whenever there's a gap there. So this is the first time there's actually a gap in this case. So we bring that number down, and I indicate that through an arrow. And you'll see we have to do it again when we have the plus 24. So we minus these brackets again. Negative x squared minus negative x squared, they cancel out. Negative 10x minus positive 2x becomes negative 12x. So we take negative 12x, we bring it up here, but just make sure that you divide by an x because that's the leading term there. So this becomes minus 12. So we actually have our expression here, x squared minus x minus 12. But the only thing that we need to do now is just confirm that we have no remainder, because that's sometimes a thing. So what we do is we just do this process one more time. Negative 12 multiplied by x, and then negative 12 multiplied by 2 becomes negative 12x plus 24. We bring the 24 down to fill in that gap, and we end up getting 0 when we minus these two expressions. So 0 here indicates that we have a 0 remainder. So therefore what we can say is that f of x is equal to x minus 2 outside of x squared minus x minus 12. And we could actually continue to factorize from here. We could just factorize this quadratic straight away. We end up getting x minus 2, and then this quadratic ends up becoming x minus 4, x plus 3. So now this is our fully factorized cubic. Now personally, I don't like doing long division with polynomials, and you can see it took a really long time to actually get to our final result. I'm going to show you a shortcut way of factorizing this once we have our first factor, which was x minus 2. Now, a lot of people actually don't like this way, but a lot of people do. So I'm just going to teach it anyway. If you like it, take it on board and try it yourself. If not, just stick to the normal long division way. So we found out that when we substitute in 2 into f of x, we end up getting 0, which meant that x minus 2 is a factor. Now, from intuition, we know that a quadratic is going to be remaining in this case, because we see that we have a linear something multiplied by some sort of expression or polynomial to get something that's cubic. So this is a degree 1, multiplying with a degree 2 gets a degree 3. And you can see that the leading term is x cubed. And there's only one way of getting x cubed, is when x multiplies by x squared during expansion. So we know that x squared is going to be the leading term in our remaining factor here. Now we could do exactly the same thing with the constant at the end. We have negative 2 multiplied by some sort of constant is equal to positive 24. Now obviously that number has to be minus 12. So this number is minus 12 here. Now there's only one more term, which is the hardest part. It's the middle term here. And the reason why it's the hardest part is because there's 2 ways of producing an x term. So we have, imagine when we're expanding this, right? This is going to be something x. We just don't know what that value is yet. Now I'm just going to change to a different color just to make this clear. When we expand, the reason why we knew that the reason why we knew that this was going to be x squared was because there's only one way of getting x cubed. It's x multiplied by x squared, because we know that this has to be a quadratic. And same thing with the minus 12. We know that this has to be minus 12 because there's only one way of getting the positive 24. It's when this constant multiplies with the constant that's in this slot here. Now, for this one, it's a bit more complicated because there's actually 2 ways. Let's just focus on the minus 3x squared, right? Now there's 2 ways of getting x squared when we're doing this expansion. It's this multiplied by this, and then it's also this term multiplied with this term. Because you can see that we have minus 2 multiplied by x squared, and then we have x multiplied by something x. But we just know that they have to add up to negative 3, right? Because that's our final result in our original polynomial. So we can see that this produces minus 2x squared when we do that multiplication, and then whatever is remaining in this gap here, or whatever is remaining from this multiplication here, has to force this to add up to negative 3. So we know that this one has to be minus x squared, because minus 2x squared minus x squared equals minus 3x squared. So therefore I know that this is just going to be minus 1x in that bracket to force it to be minus x squared minus 2x squared when we expand it to get minus 3x squared as a result. So this is an alternative way of getting the same expression that we got from long division. Again, there's actually no benefit of one way versus another in terms of one way you have to do and one way you must avoid. You could do either way you want. I prefer this way because I see this as quite an intuitive way. When I explained it, you might have understood it well, you might have not. If you didn't understand it well, stick to the other way. And if you don't like long division, stick to this way. Either way, as long as you get your final answer, then you're good to go.